So we'll look at a way to model exponential growth and decay. And this function here, f of t equals f sub 0, that's read as f sub 0. And the reason we say sub is it's f subscript 0 times e to the kt. So f sub 0 is a number. Okay, so the first thing I want you to realize is that f sub 0, e, and k are numbers. T is a variable. Okay, that's important to realize. So exponential growth and decay can be modeled with this function. So we'll look at two different cases here depending on the value of this k. One where k is positive, the other where k is negative. So here we're going to look at graphs of each of these. One where k is positive, I'll graph that here, and over here if k is negative. And in either case the function is f of t equals f sub 0 times e to the kt, and the same thing over here. I've labeled the axes. The horizontal axis is the time axis, the t axis, because remember t is the variable. And then the y-axis is f of t, or the value of the function, and that can represent different things in each case. Okay, so first of all, you might notice that if you plug in t equals 0, time being 0, this becomes, so if t is 0, you get f of 0 equals f subscript 0 times e to the 0 power. E to the 0 power is 1, so this equals f sub 0 times 1, which is just f sub 0. So in other words, whenever x is 0, y equals f sub 0. Okay, and that's true for either case. So over here I will simply mark f sub 0 there and put a point, and over here I'm purposely going to put it way up here, so that'll be our y value over here. They're the same in each case, but I put them in different places for a reason. Okay, so if k is positive, what that means is we have growth. So as we move to the right, our function gets bigger if k is positive. If k is negative, we have decay, which means our function gets smaller. And you can imagine if something's decaying, it's never quite going to reach 0, so we end up approaching this asymptote on the x-axis, this y equals 0 line. Over here there is no asymptote because the growth is unlimited. It's growing exponentially. Here we're decaying exponentially, which slows down over time. Okay, so that's the idea. We start at f sub 0. So what we can do is we can call f sub 0, it's a number, and in fact it is the starting y value, or the y value at time 0. And something important to realize about this statement at time 0 is, well, for time 0, that's you get to decide when you start measuring your y values. So whenever you click start on the stopwatch, that's going to initiate your initial y value, your starting y value. Okay? Alright, k is the other constant. We know e is just a number that always is like 2.71828, etc. K is a number also. The bigger k is, the faster this change happens. Okay, so you might see something like that, but it is a rate. The higher the rate, the faster the change. The higher the rate, the faster you're going to drop here. So it's a rate. And for example, if you have a growth rate, so this is an example, if your growth rate equals 27% per year, then that means that k is positive 0.27, because 27% is 0.27, and your time is measured in years. Okay? If you have a decay rate of you could say negative 27% per year, then it'd be the same idea. K would still be, it'd be negative 0.27 because it's decaying. It's a negative value. You'd be decreasing, and your time would still be years. Okay, so your rate can tell you your time, how your time is measured, and it will give you your K value. Okay, so again, the bigger the K value is, the faster these things change. Okay, I want to mention one other thing, so I'm going to get rid of this to create some space here. In either case, this is a nice property of exponential functions, and that's exactly what these are. The time to, in the case of growth, the time to double or triple or multiply by 4 or whatever, in the case of growth, is the same regardless of start value. Okay, so for example, if I start at this time and I go to this time, let's say this is 2 years, this is 4 years, if my y value from here to here doubles, then I know every 2 years my y value is going to double. If in this time the y value triples, this y value is multiplied by 3 to give you this y value, then I know every 2 years my y value triples. Okay? Now in the case of decay, you could say instead of doubling or tripling, you could say time to half or third or any other fraction is the same regardless of the start value. So if I start here, let's say I have 1 year, and here I have, let's say 1 hour and 2 hours, and my value is cut in half, then that means every 1 hour my y value is going to cut in half. Or if this was cut by a third, then I could say every 1 hour my y value cuts by a third. So that's a nice little property of these exponential growth and decay problems. Something else worth mentioning is growth is commonly used for population growth. Anything that grows continuously, and of course since this goes on forever upward, population grows continuously, and we'll introduce the word uninhibited, meaning you never run out of food or space, that sort of thing. So population growth, when it's not inhibited, grows exponentially. And over here we've got decay, and that can be seen a lot with decay of radioactive substances, things that decrease continuously will sort of do this kind of thing. So that's exponential growth. If your K value, your constant rate up here is positive, you'll have growth. If your K value or your rate is negative, then you'll have decay.